Now this equation can be directly integrated. So it is d of x square average is 2 times a times we can actually write it like e to the power minus zeta by m into t plus kbt by zeta dt. So we'll integrate this one. Now before integration we could also figure out that what is the value of this constant which is a, this constant, and that we can set very easily, like we know that from initial condition that at t equal to 0 we can take x equal to 0. So that will give us the left hand side will be 0, and then that is equal to a times e to the power minus 0 is 1 plus kbt by zeta. So that will give us a is minus of kbt by zeta. So that we can easily incorporate here and then do the integration. So the limits are again at t equal to 0, x is equal to 0 at t is any arbitrary time. So the position is x, and then we'll get after we put the value of a, we'll get x square average is equal to twice kbt by zeta. So you can actually check this integration times t minus m by zeta times 1 minus e to the power minus zeta by m into t. So this gives the mean square displacement. I mean, this is the full analytical solution, but we can now approximate, because as you can see here I have a exponential term, and you know that e to the power x is nothing but 1 plus x plus x square by 2 factorial, which is 2, and this way we can actually write the series, and we can truncate it up to certain terms because we can see here that it is basically zeta divided by m. Now m is the mass of the particle. If the mass of the particle is large, so then actually you can make this approximation and you can ignore the higher order terms. So if we do that, what we will get is twice kbt by zeta and t minus m by zeta, and then within parenthesis you have 1 minus. So e to the power minus zeta by m times t will be, so x is basically minus zeta m by t, 1 minus zeta by m into t plus zeta square divided by m square into t square, and there is a 1 by 2. So up to that point we are truncating the series. So we can actually put the values here, and we can see this 1 actually will get cancelled very easily, and then this minus sign becomes plus here, plus zeta by m into t, and then the plus sign becomes minus here, it will be minus half zeta square by m square into t square. So we can actually again arrange it twice kbt by zeta, and this 1 gets cancelled. Now I am actually multiplying by m by zeta. So this actually cancels with this zeta by m. So what I will be having is the first term is t minus t. So that t also gets cancelled, and then what we will have is we will have a plus sign here, and the m by zeta actually gets cancelled with 1 zeta by m, is zeta by m squared. So I will be left with 1 zeta by m times t squared. So this t will again get cancelled. So what ultimately we will get is we have another zeta will get cancelled with this zeta, as you can see, this one and this one get cancelled. So what ultimately we will get is, and also there was a 2 factor, I forgot to include that. So there was a half factor, and then this 2 also gets cancelled, this 2 gets cancelled with this. So ultimately we will get an expression for the mean square displacement as this. Let's write it in the next page. So what we will get is x square average is kBT by m into t square. Now what we have done here is basically known as the ballistic regime, in the sense that if in this formula, as we can see, if what we have made an approximation that in the very small time scale, this will be correct, in the sense that if you remember that when we made this approximation, we wrote that this e to the power minus zeta t by m, that ultimately we took the 3 terms, right, and these 3 terms means actually this t by m is much less than 1 when m is large or time is very small. So in that limit, when t is going to 0, so we have actually the mean square displacement going as t squared. So this regime is known as ballistic regime. When actually t goes to 0. Now if we think about the other limit, in the sense that t is very large, then actually we will what we will see here that this value, the kBT by m to the power half, so we can actually write it in this way. So you can go back and look at your exponential. So if the time is very large, so or t is much smaller than m by zeta, so this is this actually corresponds to the ballistic motion, as we have seen here. So it will be zeta t by m much less than 1, or t by t is much smaller than m by zeta. So when time actually goes to 0, I mean very short time scale. Now in the other time limit, when actually t is much higher than m by zeta, so then we can actually assume that in this equation, that x square average, you can easily figure out what the result will be. You can easily figure out from this equation, where I have x square is equal to the original equation, that is twice kBT, this equation where we had a full analytical equation, and if we do not make that approximation, then actually you can keep that, and then you can show that in this time regime it will be nothing but twice kBT. So because the zeta will cancel out, it will be something like twice kBT by zeta into t. Now this regime when is valid when actually t goes to infinity or in the long time limit, and this is known as the diffusive limit, or in the Brownian limit. So it's in the diffusive regime. Now this mean square displacement equation, again you can actually figure it out, and we'll show you in the handout how basically it comes. So do not make this approximation, that do not truncate this series up to this point, and then you can actually ignore the entire term e to the power minus zeta by m into t, because that is a very small number now, and then because actually it basically goes as e to the power minus infinity, and because t is very large, and then what you can do is that you can just keep the first term, which is 1. So it will be just t minus m by zeta, but again t is very large. So all you will be left with is this term. which is just T. So that's how this equation you get. Now this was shown by Einstein, but he also predicted that at a very short time you will have a ballistic regime where actually the mean square displacement will go as T squared, and at a very longer time you will have a diffusive regime where actually mean square displacement will go with time. Now we can actually go back and use the mean square displacement formula that we just developed, in the sense that if you remember that we were talking about diffusion, and there we solved the RMS deviation. So we are using a Z notation. In this case I will use X notation because X and Z are just arbitrary. So this RMS deviation or the root mean square deviation, X RMS, square of that is nothing but X square average. In this case X RMS is X square average minus X average squared and the square root of the entire thing. But it is basically root mean square deviation, but in this case the X average we are taking it to be 0. So that's why it is nothing but the X square average and square root of that. So that's why I am writing it directly as X square average, and that we already know from the diffusion equation, which we already saw a little bit earlier. It goes as twice dt to the power half. Now what we got just now in the diffusive regime, X square average is twice kBt by zeta into t. So we can actually equate these two equations, and we will get that this is if I take the square of this quantity, so it will be just there will be no half, because this half is only for the RMS thing, and we are taking the RMS squared. So what we see here that twice kBt or twice dt is nothing but twice kBt by zeta into t, and now you can get a very handy expression for the diffusion coefficient, which is kBt by zeta. Now you can actually further use the expression for zeta. Zeta is again a frictional coefficient. Now you can use actually Stokes formulation, where he said for a spherical particle this zeta or basically the force which acts on a Brownian particle or a spherical Brownian particle will be nothing but minus zeta into its the velocity, because we use this force. If you remember that we wrote that m into acceleration, mass times acceleration, is this opposing force, which is a frictional force, and frictional force for a spherical particle will be nothing but minus 6 pi eta a into v, where this a is the radius of the particle and eta is the coefficient of viscosity. Now we can see that the diffusion coefficient, now we can connect it to the coefficient of viscosity, and that's a very interesting equation that we can write that it is kBt by zeta, and in place of zeta we can write 6 pi eta into a. So this is from Stokes equation, and this force is nothing but the frictional force for a spherical particle. Now we can move on, and we can actually use this concept of diffusion, which we just have developed, to understand what will be the general formulation of any reaction in solution, because ultimately we want to express the rate constant in a solution which are actually diffusion limited, in the sense that the rate determining step is basically the overall rate is basically determined by how these two species or two reactants are encountering each other. and we are saying that we can assume that every encounter can lead to reaction, which means the reaction is not limited by the encounters, because whenever they approach each other they will definitely encounter, and every encounter will give reaction. However, now we are limited by how many encounters are happening, because these two reactants are just like two partners, and they have to just find a partner in solution, because they are moving now in a crowded environment and they are basically diffusing. Now we can actually develop a model based on that. So the language which I just told is something like already known to you. I have two reactants, say, and then we are forming some complex which I already wrote many times, and then we have some forward rate, so we call it as a encounter rate, and then there is an escape rate, and then this AB in the second step actually forms a product, and this is basically the rate of the reaction, rate of product formation. Now we know actually under steady state approximation we can write the rate of product formation. We have done it many times, and that is nothing but K, the reactive rate constant, times the encounter rate constant divided by the escape rate plus the reactive rate times A times B. So this is just the bimolecular reaction in solution. It's the same formula which we use for gas phase reaction. Now, and again, if you remember that if we think that this Kr is much smaller than the K escape, which means the reaction is basically limited by the reactive rate, then actually overall it's a bimolecular reaction. So I'll have the effective rate constant as something like Kr K escape K encounter divided by K escape. So which means actually the rate is limited by the last step. So the encounters are basically small, but we are not considering that limit. We are considering the other limit where the reactive rate is much faster than this escape rate, which means the effective rate is nothing but, as you can see, if I keep the Kr in the denominator and ignore the K escape, then actually the Kr gets cancelled with the Kr in the numerator, and all I'll have, the reaction rate is dependent on the encounter rate. So this regime is basically the diffusion controlled regime, because it's the encounter rate that matters. So it's the diffusion controlled regime. So we are going to actually formulate that now. Now the question is how will you formulate it? Suppose we have two reactants A and B, and what we are going to ask is that, okay, fine, so then there will be a flux of A molecules into B, and then there will be a similar flux of B molecules into A. So overall the way it will look like is something like this. I have say a molecule of A, and then suppose I am writing the B molecule in a different color. Suppose this is the B molecule. So there is a radius within which a sphere within which the A and B, the B should be there, otherwise the reaction will not occur. So this basically the we are again considering this as a hard sphere model, just like we did. But the question here is that this B is coming from a distance which is let us say at a distance r, and then what we can think that there is a bigger radius from where this B is coming from. But so all we have to do is basically calculate what is the flux of these B molecules towards A, or equivalently what is the flux of A molecule towards B. So if we can calculate that, then we are done, because that will be connected to my rate constant, because now it is limited by the diffusion as we have seen it. So encounter is nothing but basically how they are finding the partners each other. Now the interesting question which we can ask here is this, that okay fine, I have a molecule with B and B is coming, but then what is the symmetry of the problem, in the sense that it's not like happening in the two-dimensional plane as I have drawn here. So there is a B molecule, like let's say there is a molecule at the center, the way I have drawn it. Now the B can approach in any direction regardless of the angle of approach, which means actually we can actually think the entire problem in a spherical polar coordinate. That is number one. And number two is that as the B and A encounter, and we are assuming that K reaction is pretty fast, meaning that every encounter is giving a reaction, which means actually there will be a depletion of B molecules around the A molecule, which will create a concentration gradient. Similarly, in this picture actually it's in a relative frame where actually A is static and B is moving, but you can think in the other way, that A are also relatively moving to the B, and then which means actually the concentration of A around B will also deplete, which will create a concentration gradient for A also. But it is the same reaction, because A and B are basically encountering and the product is being formed, and as a result both concentration of A and B are depleting. So since it is the same mechanism, the gradient for A and B also you can assume to be identical. Now in order to approach this problem, let us first start with our formula for reactive flux. In this case we will just use the flux and we will connect it to the reactive flux later. So the flux, as we know, is let us say flux of B molecule, that we are writing as minus JB, because there is a, in the flux equation there is a minus sign. I am writing the minus with the flux equation, and that is basically diffusion coefficient of B times, now this flux I am considering now in 3 dimension. So this is a vector quantity, I should use a underscore or boldface J of B. So I am just using a underscore for vector, and this is the diffusion coefficient, and then I have a 3-dimensional gradient of concentration of B, and which this concentration is now dependent on r, theta and phi. And similarly I can also write it for A, the flux, which is a vector quantity, again is nothing but the diffusion coefficient of A and the gradient of A as a function of r, theta and phi. Now what is this gradient? Now this gradient again is a vector quantity, which is I del x plus j del y plus k del z, which is written in a Cartesian coordinate, rectangular Cartesian coordinate, where I, j, k and the unit vectors along x, y and z direction. But we are more interested in solving this problem in spherical polar coordinate, and in there the del takes the form like the unit vectors, if I write it as a, b and or a suffix phi, or we can write it any, we can choose any notation. Let's say let us do it as L, M and N. So L is basically the unit vector along R, so it will be A del R, plus M is the unit vector along theta, so it will be 1 by r del theta, and N is the unit vector along phi, which will be 1 by r sine theta del phi. Now this transformation probably you have seen, you have to write xyz in terms of r theta phi or r theta phi in terms of xyz, and then take the partial derivatives. And then you can actually get this gradient in the spherical polar coordinate. This you have probably seen when you did some problem in spherical polar coordinate, for example the hydrogen atom problem. So they are actually use this, they are actually use the del square also, which we also need subsequently. Now what I am saying here is that now I have a flux of A molecules towards B and B molecules towards A. So the net flux will be basically the addition of the two flux, and this net flux I am keeping to be basically a positive. So that I define the next flux not as Ja plus Jb, but actually negative of Ja plus Jb, so that I keep the net flux notation to be positive. So it will be very straightforward. It will be basically dA plus dB times the gradient of B. Now in this case again remember that I have assumed that the gradient of B is basically identical to the gradient of A, because the gradient is being created by the same mechanism. When A and B are encountering, both vanish and the P emerges, and that is why the gradient is formed, and so the A and B gradient should be basically equal. That is an approximation, but it is a very valid approximation under this model. Now what we can say here is that so the A and B are basically coming, and there is a suppose at time 0 basically the reaction starts and A and B are approaching each other, and then once they encounter there is a concentration gradient which sets in, and then again more and more A and B actually approach to each other, and there will be a reaction, and sooner or later there will be a steady state which will be reached. Now before we started at t equal to 0, everything had a bulk concentration, meaning the B at t equal to 0, so we can approximate at t equal to 0, the B is basically equal to B of bulk. We are just writing it as a hyphen suffix at as bulk, and similarly A was also A of bulk. So these are the basically bulk concentration, and these bulk concentrations do not change over time because this is just a bulk concentration, and then over time what is happening, there is a local concentration changing. So we are assuming that there is a reactive sphere, something like we have drawn here. So this is the reactive sphere, and this reactive sphere, outside this reactive sphere there is basically there is bulk. So when this r, or the radius of the encounter, or the distance between these two pairs, reactant pairs, is very large, when r tends to infinity, this A will tends to A bulk, and B will also tend to B bulk, and A and B bulk are not influenced by the reaction, which both of them are basically independent of time. That's an assumption we are using. Now we can actually use the fixed second law in the 3 dimension, because we actually showed it for 1 dimension case, but it is the same thing. And then basically we are saying that since all the encounters are giving me reaction, the reaction encounter is nothing but identical to the diffusive encounters itself, and for which we have a formula which is dA plus dB into gradient of either A or B. We are writing it in terms of B, and again B is dependent on r, theta and phi. Now we can actually say that what is the time derivative of this concentration, what is dB dt. Again B is basically the local concentration, not the bulk. Whenever we are using the bulk concentration, we will write suffix bulk. So dB dt, so that we know that we are basically extending the 1 dimension to 3 dimensional problem. That is basically the gradient of the flux itself, the joint flux, which is a time dependent quantity, and that is nothing but dA plus dB. Now J itself, as you can see in the earlier expression, that it is a gradient of B. So it will be now actually del square of B of r, theta and phi. Now the question is, what is the form of del square in, like we have already talked about the form of del. Now in spherical polar coordinate, the del square is can be written as del 2 del r2 plus 2 by r del r plus 1 by r square del 2 del theta 2 plus 1 by r square cot theta del theta plus we will have 1 by r square sine square theta del 2 del phi 2. So this is the overall spherical polar one, and the Cartesian one is very straightforward. It will be if I write the del square, so it will be just del 2 del x2 plus del 2 del y2 plus del 2 del z2. Now see here that del is an vector quantity, because it depends on 3 vectors I, j and k unit vectors, but del square is a scalar quantity, because del square is nothing but del dot del, and if I consider del to be a vector, this del square is a scalar because it's a dot product. Now we can actually think that all this B, or the concentration variation, is actually varying radially independent of the direction. So all we have to consider here, so that del theta or del phi, or those are basically 0, which means there is no angular variation, as we said at the beginning, and all the variation is basically the radial variation. So we can right away, instead of writing the del square in the full form, we can just write the only the radial coordinate variation. So let us just write it. So del B del T will be dA plus dB times I have del square of B. So you see here that del square, I'll just consider these first two terms. So it is del 2 del R2 of B plus 2 by R del R of B. So when the steady state is reached, this should be 0. When we have reached an equilibrium, that the reactions forward and reverse reaction happening at a same rate, and you have a steady rate of product formation. So under the steady state, because it's all under steady state approximation, we can think that the time derivative of B is basically 0, which means actually if what the way we should think about it is that there is a bulk concentration which is very high, and then there is a reactive zone, and within the reactive zone actually the reactants are continuously being flown. Now which means actually, of course, the reactants are being depleted in the bulk due to diffusion, but we are assuming that the A bulk and B bulk does not change because the concentration is too high, but only in the near the vicinity of A the B is changing, and similarly in the vicinity of A also, in vicinity of B also, A is changing. Now we can actually right away solve this equation, and the solution will be B is nothing but and again this B is a function of the radial coordinate. B is C1 by 2R plus C2, where actually C1 and C2 we have to determine. Now we can use the boundary condition, like we already know that if R tends to infinity, A tends to or B tends to basically be equilibrium. So we can right away see that if R tends to infinity, this term will be 0. So C2 is nothing but B equilibrium. So B is, sorry, not B equilibrium, it is basically B bulk. So we can right away write that B is C1 by 2R plus B bulk. Now what is the rate of product formation? That is what we are interested in, and we already wrote that the rate of product formation dP dt, that is basically equivalent to the reactive rate constant times the concentration of A in bulk, because we are thinking that actually B is coming, and B is basically depleting, and so the local the way I have drawn it, basically B is vanishing. So the A concentration, we are saying that it's not changing, because at you can think it like this, that there is a bulk A concentration, and then only the B is approaching, because it's all relative motion. So the for B actually we have to consider the local concentration of B, and that we already know that this is nothing but, if I just integrate the B equation. Now you know that what is the B equation? B equation is nothing but it should be, the rate should be the flux, which is the reactive flux, which we already have talked about, and then I will have basically a volume within which this flux is happening. So flux is again basically the flow per unit area per unit time, and then I have to also consider the volume. Now currently the volume I am considering, the reactive volume or the reactive zone, is basically a sphere with a radius smaller. So the overall volume will be 4 pi r square. So this is basically the number of how many A molecules are there, or how many B molecules are coming, that we are calculating. So it is nothing but multiplied by 4 pi A squared, that is the volume, times the A bulk. A bulk we are not touching. Now we can write the expression for the reactive flux, which we have already got here, J reaction. So what we can write is, proceeding from this relation. So in the next step we are writing as Kr, which is the reactive rate, or the basically the final step rate, times the A bulk actually is on both sides, but we are just keeping it first. I mean, we'll see what it will have. A bulk times B, that is basically equal to A bulk times 4 pi r square, and instead of flux, right, we are now using dA plus dB. The reactive flux is exactly equivalent to the overall flux, and then I have the time derivative of B, and which we just solved. So this is coming from the Fick's second law of diffusion. And now the interesting thing is that now you can actually write down the equation for the B bulk. So we can actually divide both sides by A into R square. So let us just write it, dividing both sides. We could have removed the A bulk right in the beginning, because you can see that it's a common term. So dividing both sides A bulk, and then I'll also divide it by R square. So what you will get is a little bit compact form, which is Kr. I have the B is the local concentration again, and then what I have is I have dB here. So this should not be the time derivative, this should be the space derivative, because it's just the equation for the flux, as you can see here. So this flux is basically the how things are approaching with each other, and that is basically the concentration gradient, dependent on the concentration gradient. And since this is only radially varying, so this is just del R of B, but we are not using the del notation right now, because it is independent of theta and phi. So we can actually write it as d dr, because the only variable is special variable is r. So we can actually write it as dr by r square is basically equal to 4 pi r square, already we have removed, dA plus dB into dB. Now what we are going to do is basically, now of course we are going to integrate this equation, and remembering the fact that if I integrate it at say at a particular distance, which is let's say at a distance, let's say r, which is a which actually is this distance, because this distance is important, because all I have to calculate is what is the basically local concentration and flux at that point, because at that point these two species are basically touching each other. So capital R is basically the radius, or the capital R is basically the radius of A plus radius of B. So that we have already discussed in many situations, like when we talked about the excluded volume in Van der Waals equation, or say when you talk about the reaction in gas phase, or basically we derive the mean free path or collision in gas phase, we always talk about the cross section. And this cross section is nothing but in a linear case, so the molecule will feel a cross section, and we say that it is basically the cross section. I can actually write it as an area, circular area, where the radius is basically the addition of the radius of the two species. And it makes sense, because if we just make that condition to happen, then the collision will happen. But if the distance is more than this critical distance, these hard spheres will not touch each other and there will be no collision. So the lower limit is R here, and so basically it is in this case the lower limit is at B at R, and which happens at a location R, and at infinite distance, or infinite distance, this B will be nothing but equivalent to B bulk, which we already argued. Now if we do this integration, so it will be nothing but, it's a very straightforward integration. So what we will have is Kr. Now the B at a distance R divided by R. So I am writing actually the so this 1 by R actually comes from the integration of 1 over R square, and then I have on my right hand side dA plus dB, and then it's just an integration of B. Okay, so when I write this thing, since we are writing the local concentration as Br, let us also use this notation here. It should be Br, because if you remember what is happening here, I have a bulk concentration of A, so A is everywhere, and I am fixing the A as if A is not moving and B's are moving. Now B is coming, okay, and B actually is touching the A, and at that location I am calculating the flux of B, and then B is vanishing and there is a concentration gradient that we have already worked out. But the interesting thing is that when B is coming and it is basically touching, we have to actually consider that location, otherwise the encounter will not happen. So what we are doing here is 4 pi dA plus dB, and then we have this right hand side integration is very straightforward. It is basically B at R equal to infinity minus B at R equal to R. So that already we told that this is basically B bulk minus BR. So now this BR thing we can take common, and we can write as BR into KR K suffix R. This is a reactive rate. We could have written it as a K2 just to distinguish between smaller and this reactive R, and then I have, there's a minus sign, so it will be plus sign if we are just bringing this term on the left and adding with this term. So there is a constant which is 4 pi dA plus dB, and that on the right hand side we have 4 pi dA plus dB times B bulk. So we can now easily solve it. So this is Br. What is the value of Br? So this is basically the concentration of B in the vicinity of A, and that is nothing but equal to the B bulk, its bulk concentration, divided by this entire thing, which is if I just rearrange this a little bit, because I see that there is a 4 pi dA plus dB. So I can divide the numerator and denominator by 4 pi dA plus dB. It will be 1 plus Kr divided by 4 pi dA plus dB into R. So this is the overall expression for B in the vicinity, the concentration of B in the vicinity of A. So that we are now going to use. Now already if you remember that we that why we need that, because remember that we calculated the concentration of B, the time dependence, and then it basically reduced to another equation after we wrote the bulk form, that B at any position you can write it as C1 by 2R and plus B of bulk. So that we are now going to use that what is basically the B, because we need the values of C1 and C2 also. Now C1 you can easily calculate. Now this is unnecessary because all we are interested is basically to calculate what is the rate of product formation, and remember that is nothing but A bulk. Let us write it once again. So this is the reactive rate times the local concentration of B times the bulk concentration of A, which is nothing but, now we have already solved it, the local concentration of B. So it will be nothing but Kr divided by 1 plus Kr by 4 pi dA plus dB into R times A bulk times B bulk. Now if the encounter rate is very fast, which we actually already made an assumption that this rate is much faster than the diffusion rate, and the diffusion rate is given by 4 pi. Again, the 4 pi is coming from the spherical symmetry, it is the total solid angle. So it is dA plus dB times R. So 4 pi R is basically the volume around A. So this is the closest approach volume, and then if I multiply by the diffusion coefficient, so that if that quantity is much smaller than the reactive rate, so we can actually ignore this. As you can see here, 4 pi, this term actually we are writing it to be much smaller than Kr. So then actually we can write the overall rate expression as if I consider this entire term as the K effective or the K of this reaction. So we can actually write it as the K is 4 pi dA plus dB into R. Now how it comes, it is very easy, because as you can see that this term is in the numerator. So I will just write it as I will write it as 4 pi dA plus dB into R, because it is multiplied by 1 plus Kr, and then I will ignore that term. So denominator it will have only Kr, and this let me just show you what I am saying. So it will be Kr divided by 4 pi dA plus dB into R plus Kr divided by 4 pi dA plus dB into R. Now this term we can actually ignore with respect to Kr, so that we can write it as Kr, and this term will now go in the numerator into 4 pi dA plus dB times R divided by Kr, and this Kr actually gets cancelled. So that's how we are getting it. So this is basically the overall rate constant, which is the diffusion limited expression for the diffusion limited rate constant, and that's what we wanted to calculate. So the overall rate or the composite rate of this reaction when the last step is very fast, the Kr is very fast, we see the product basically gets formed with a rate which is equal to 4 pi r, where r is capital R, where it's basically the closest approach distance, and times the dA plus dB. So this is what we wanted to do, and to find out an expression for the diffusion limited rate constant. So this is the diffusion limited rate constant. Now we will have complications when these species are ionic species, because whenever they are charged species, so there will be a repulsion, and if they are of opposite charge, there will be an attraction. So we can actually use the same formulation, in the sense that A and B are approaching each other, and the same diffusion equation, but the only thing we have to plug in very carefully is the repulsion, and that we will see later. But just to give you a feeling that we also were deriving this time derivative, because we used fixed second law at some point, and we used basically the time derivative is 0, and then we solved for B for any position, that we wrote it as C1 by 2R, although we did not use it. And this is just to give you a feeling that how you can actually get the steady state concentration of B. But then we only solved basically the value for C1, but not for C2, sorry, not for C2. And C1 was we did not solve. Now the C1 you can easily figure out, because we have already got an expression for B at a position R. So from that actually you can actually work it out on your own. The expression for C2 that you should get, sorry, not C2, it is C1. The expression for C1 that you should get is, let me actually rewrite the earlier equation once again. So we got basically B at any arbitrary location, let's say at a location R, is nothing but C1 by 2R plus C2. So what we can say is that B at a location R is basically capital R, which actually we wrote as B suffix R, that should be C1 by 2R plus C2, and C2 already we figured out, it is nothing but B bulk. And then Br already we solved, which is this equation, and now you can see that the way we have to do it is basically I have to add one B bulk to it, and then I can easily solve for C1, and if you do it, the expression for C1 will be minus twice R times B bulk divided by 1 plus 4 pi dA plus dB times R divided by Kr. Although you did not use it, thus you can see that I can actually get the value of B, which we actually wrote in this equation, at any position. And so this is a general equation for the value of the concentration of B at any position with respect to the A. Now here one question that you might think is that why we were using in this equation when we are actually discussing the rate of the reaction, why we were using A as a bulk, because we said that why it's not a local thing. Now the concept here is that you can think that okay, so there is a bulk concentration of A and B initially at time 0, and suppose there is no reaction, we just mixed it, there is no reaction at time 0, if you can conceptually think about it, and at that time every concentration is bulk concentration. Now the A is sitting at the middle and the B is coming, and that is how we actually modeled our system. But we said that the flux actually is in both ways. So the reactive flux is actually both JA is contributed by JA and JB. But you can actually cast the entire problem in as if the A is static and B is moving. This is the same thing you do when two particles come closer together, and you say that the relative velocity is nothing but v1 plus v2. The addition of the two velocities. So it basically adds up. The same thing, the flux is also adding up here. And second thing is that so one is but then we are saying that since A is this A is stationary and everything is calculated in A's framework, so the B is approaching, and once the encounter happens, then the B is also depleting. A is of course also depleting, but then actually it is creating gradient for B, and then actually more and more B will come. That is in somewhat it's an approximation, because then the A should not be actually A, initially it should be A of bulk, but then as the A also vanishes, the concentration of A also kind of drops and it creates a gradient. But we are not considering the motion of A, we are considering only the motion of B towards center, which is basically at the center we have an A. So with these approximations, this is a more or less correct expression for the diffusion limited reactions, where actually we assume that every encounter will actually cause reaction. So the overall reaction is limited by the possibilities of the encounter, that these two species actually come close together in a crowded environment, because they are coming in a zigzag pathways, and they find A and B actually find the partner for each other, and then they react. Now in the next section we will be talking about the reaction between ions, and where we will actually move on with this particular treatment, and then we will talk about what happens when actually you consider the electrostatics. Thank you.